My project is going to explore the risk and reliability of a pressurized water reactor. Currently, 60% of commercial power generated by nuclear reactors in the United States is generated by pressurized water reactors. These reactors require that the water in the reactor vessel remains in a completely liquid state. In order to achieve this, a pressurizer is utilized. In addition to the pressurizer and the reactor vessel, a pressurized water reactor contains 4 other important subsystems. These subsystems are the steam generator, the turbine, the condenser, and the generator. The pressurizer maintains the pressure of the water in the coolant channels by manipulating a large bubble of gas. Because this bubble of gas is directly connected to the coolant channel, by altering the pressure of the gas, the pressure of the water can also be changed. As water in the primary coolant channel is pumped through the reactor vessel, it gains heat from the fission process occurring in the reactor. This hot water is then pumped to the steam generator, which acts as a large heat exchanger between the primary coolant channel and the secondary coolant channel. This means that the irradiated water from the core is kept separate from the electricity generating portion of the facility. The secondary coolant water flows from the steam generator to the turbine. In the turbine, the steam is allowed to expand, thereby turning a massive array of blades connected to a central axle. The turning of this axle causes the rotor of the electricity generator to turn. The electricity generator works on the principles of Faraday's law, which states that a changing magnetic field can induce a current in a wire. In this generator, an electromagnet is created by wrapping wires supplied with DC current around magnetic steel, and these electromagnets are located on the outside perimeter of a large wheel connected to the rotor. As the rotor turns, these electromagnets pass by conductors located in the stator, which is not turning. This creates an AC current in the conductors, and this current is passed through a series of transformers before it is ready for the consumer. After the steam has passed through the turbine, it is directed to the condenser. The condenser is another large heat exchanger. It takes steam from the secondary coolant channel and returns it to its liquid state using a third reservoir of water, typically a large river or lake. After being pumped through the condenser, the water from the tertiary reservoir is returned to the environment at a slightly higher temperature. The water in the secondary coolant channel is pumped from the condenser back to the steam generator, where it can continue to extract heat from the primary coolant channel. The most important component of a nuclear power plant is the reactor core, contained in the reactor vessel. In a pressurized water reactor, the fuel rods contain uranium pellets enriched to roughly 5% uranium-235, contained in a cladding normally made of a zirconium alloy or stainless steel. These fuel rods are typically 4 to 5 meters in length and are grouped into bundles. These bundles are removed from the core at regular intervals to refuel the reactor. In a pressurized water reactor, water is both the moderator and the coolant. For those of you who are unfamiliar with the term moderator, it refers to a material capable of slowing neutrons down. When neutrons are born in a fission reaction, they have a large amount of kinetic energy, and this reduces the neutron's chance of causing a fission event in a uranium-235 atom. Moderators are employed to take this kinetic energy away from the neutron, so that it can cause a fission event. To stop the self-sustaining nuclear reaction in the core, control rods are employed. These rods are normally made of a neutron poison, which means that the atoms of the material are very likely to absorb neutrons. If neutrons are absorbed in these materials, they cannot cause fission events. In the case of an emergency, these control rods can be dropped into the reactor, even if there is no external power, because the control rods are suspended above the reactor using electromagnets. If there is a power failure, current to the magnets will cease and gravity will pull the control rods into the core. During normal reactor operation, these control rods can be manually inserted to different depths within the reactor by an operator. In addition to the 6 systems already described in this video, there are 3 more general groups of systems which are necessary for the safe operation of a nuclear reactor. These subsystems are the pumps responsible for moving water in the primary and secondary coolant channels, safety features to minimize the probability of a dangerous nuclear accident, and an expansive system of gauges used to measure the characteristics of the reactor. The operation of the pumps is self-explanatory, so no further detail will be explored here. Safety features are grouped into passive and active categories. A passive system requires no input or external power to function properly, whereas an active system does require input from an operator. The specifics of these safety systems will be further explored in future discussions. Gauges are employed throughout the facility to measure water pressure and temperature, power output of the reactor, and many other attributes of the reactor. Many of these readings are displayed in the control room to assist the operator. This concludes a brief overview of a pressurized water reactor.